What up, what up? This video goes over the first three sections of AP Pre-Calculus. Change in tandem, rates of change, and rates of change in linear and quadratic functions. So let's just jump right into it. Again, this is an AP Calculus concept, and this is following the AP standards found on College Board. If you have an AP class, your teacher is going in this order. The first thing we're going to talk about is concavity. Now, I know what you're thinking. Concavity? Well, I speak Spanish. Does that mean I need to go to the dentist? Concavity looks like this. It's basically curves. All right, and we have two types of concavity. This guy is called concave down. It's a bowl that's upside down. A very popular haircut nowadays called the Edgar kind of looks like this. We have another type of concavity. This is concave up. Now let's explore what we're dealing with here. With concavity, we see symmetry. So let's draw lines of symmetry straight down the middle of our concave down and our concave up. Now, what we have with concavity is we're pretending that we are on a skateboard, either going up a hill or going through like a half pipe or something like that. And while we're on our skateboard, if I were to start going up this hill, on concave down, and I start here, it represents like a positive slope. And as I go up the hill, I kind of flatten out. And then at one point, I kind of hit this peak, and then I start going down the hill like so. I'm not a fan of what I did here, so let me get rid of you and try to flatten you out like that. That's much better. Erase. Now, this is concave down. On the left side of concave down, we're noticing a few things. On the left side of concave down, my rate of change, so right off the bat, we're talking about rate of change. Now, remember, it's very important to understand that rate of change is the same thing as slope. So all of these slopes that I drew out here is also the same thing as rate of change. On the left side of concave down, my rate of change is positive. Every single time, my rate of change is positive. But this is what I'm noticing. As I'm moving from the left and to the right, my rate of change is flattening out. So if this is like a slope of up 3 over 1, and if this is like a slope of up 2 over 1, and that's a slope of up 1 over 1, and that's a slope of 0 at the tippy top, my rate of change is positive, but it's also decreasing. So those are two very important words. A rate of change being positive means it just looks like this. A rate of change is decreasing means that over time it's flattening out and going from positive to 0. Now, similarly, on the right side, I can look at my skateboard going down the hill. As it's at the very tippy top, it's 0. But the moment I move away from the tippy top, it's now a negative slope. So the rate of change on the right side of concave down is negative. On the right side of concave down, my rate of change is negative, but what I also see is that my 0 becomes like a negative 1. And then becomes like a negative 2, and then becomes a negative 3. So on the right side of concave down, my rate of change is negative, but it's also decreasing still. So what we've learned so far is that when my rate of change is decreasing, it's concave down no matter what. On the left side of concave down, it's a positive slope. It's a positive rate of change. My function is increasing. However, my rate of change is decreasing on concave down. Understand the difference between the two. My function is what is the graph doing. My rate of change is what is the slope doing. Huge difference. Now, if you're like, wow, sir, you really drew that too big and too close to concave up. I did it on purpose. And here's why. If I look at the left side of concave up, I am now a skateboarder going into a half pipe. So once I drop into the half pipe, I'm a steep negative slope, okay? And then it's still negative, but the moment I hit the very bottom, it's zero, it's flat. And then once I go up the hill, it's positive, some more. So on the left side of concave up, I have a negative slope, which means my rate of change is negative. However, on the left side of concave up, I go from like a slope of -4 to -3 to -2 to -1 to 0. My negatives are starting to approach 0, which means my rate of change for the left side of concave up is increasing. Ooh, that's different than what I've seen before. Okay. Now the right side of concave up, my rate of change went from negative, it hits the bottom, and then starts being positive. So on the right side, my rate of change is positive. On the right side, my rate of change is positive. However, what is my rate of change doing? Well, my slope, as I continue moving to the right, is a positive slope, steeper, positive, which means on the right side, my rate of change is increasing. So what we've learned here is that when it's concave down, the rate of change is decreasing. Okay, it starts going positive, then getting smaller. For concave up, it starts out at a very negative, steep slope, which means very negative, and then gets positive. Understand the difference between, oh, my function is decreasing, which means it's just going down. Okay, negative slope, versus my rate of change is decreasing, which means it's getting smaller. Big difference between the two. Now, the other thing we need to know about concavity is whenever we have a change in concavity, so right now I'm concave down and then boom, all of a sudden concave up, that change in concavity right there has a name, and it's called an inflection point. A change in concavity is called an inflection point. If it doesn't change from concave down to concave up, or if it doesn't change from concave up to concave down, then it's not an inflection point. Okay, if it's a straight line, it doesn't have concavity. Okay, so make sure we're understanding that concavity is this curvature. Okay, and we need to make sure that whenever we are given a visual, we understand the difference between something that's concave and something that's not. So that's concavity. Okay, that's thing number one that we need to look at. Thing number two that we need to look at is the average rate of change. Now, if I were to draw you a picture, okay, and, here's just a very typical graph. If I were to draw some curved line, looks something like this, right? In pre-calculus, we deal a lot with intervals. Okay, so interval means on the x-axis, I have a spot right here and a spot right here. What's happening in between? Okay, so let's call the first spot A on the x-axis. This is an x. And let's call the second spot B. Okay, on the y-axis, also known as the f of x axis, if I plug in A, I'm going to get this guy right here. So that lines up with f of A. If I plug in B, that lines up with this point right here on the line, which lines up with f of B. Now, rate of change, we mentioned a bunch of times in the last slide, is slope. The average rate of change is the exact concept. However, we view slope as a straight line. So the average rate of change is the straight line change between point A to point B. So if I can successfully draw this and not make it look stupid, an average rate of change is the straight line going from A to B. And so if I was looking at a graph, I should be able to count rise over run and figure out what my rate of change is. However, if I'm not given a graph, or if I need to show calculations, what I normally might do to find rate of change is give you the slope formula, which is this guy right here. However, in AP Pre-Calculus, we rarely use the slope formula. Instead of x sub 1, y sub 1, we use the point A, f of A. And instead of x sub 2, y sub 2, we use the point B, f of B. So if I wanted to find the rise over run here, what I would do is do f of B minus f of A over B minus A. It's the same exact thing as the slope formula, but more AP Pre-Calculus-y. Okay? Average rate of change. And again, the average rate of change gives me the slope, which gives me a rate from A to B if I'm dealing with a curved line. Okay? And even if I'm not dealing with a curved line, it does the same thing if it's linear. It's just not as useful. All right, let's talk about linear and quadratic rates of change. Now, a linear function, you know what that is. It's a perfectly straight line. A quadratic function is a parabola, which means things change. Okay, the patterns are not as exact as what they are for linear. And normally with these types of problems, you are going to be given some type of table or some type of chart of x or y values, but I'm going to use f of x because it just looks nicer. Okay, so I'm just literally making this up on the spot. This doesn't mean anything special. The fact that I started at -2 means absolutely nothing. And I'm going to do -4, -2, -1, -1 again, -2, -4. All right, now, you probably learned back in Algebra 1 or 8th grade math that if it's linear, that your pattern, as long as these guys go up by the same number, your pattern over here is going to do the same exact thing. Now, AP Pre-Calculus uses an absolutely terrible phrase that I'm going to try to pull out of a hat, and I believe it's called consecutive input value equal interval stuff. Okay, and when you see that phrase, consecutive input values equal interval, I think it's actually consecutive equal interval input values. I think I nailed that. What that means is x going up by the same number every time? Yes, which means they're consecutive equal interval input values. Terrible, but that's what that means. So over here, x is going up by 1 every time. So if it's linear, whatever is happening over here has to happen the same every single time. So let's test its linearity, if that's even a word. To get from -4 to 2, I add 2. To get from -2 to -1, I add 1. To get from -1 to -1, I do nothing. To get from -1 to -2, I subtract 1. To get from -2 to -4, I subtract 2. Now, is this the same exact number every single time? No, then it's not linear. So now if we're going to test how quadratic it is, we're going to do the same exact thing with these numbers. How do we get from 2 to 1? Subtract 1. How do we get from 1 to 0? Subtract 1. How do we get from 0 to -1? Subtract 1. How do we get from -1 to -2? Subtract 1. So what this -1 means, right, is if I wanted to find a pattern here, then every time I bump up to the next output value, I just subtract 1 more. I add -1 more. So the next guy, I'm going to go from -4, I'm going to subtract 3 to that. And I'm going to go for whatever that number is and subtract 4 from that, and so on and so forth. Okay, but what we got here, since the number for quadratic was the same throughout the whole time, we have ourselves a quadratic. And the way you would see that in an AP exam is, which of these statements is true? And the solution would be, this is quadratic because the consecutive equal interval input values of the rate of change of the rate of change. So here's your regular rate of change. So this would be considered the rate of change of the rate of change is the same. The verbiage is terrible. That's what makes this an AP exam. Okay, rate of change of the rate of change. Actually, I think they say rate of change of the rates of change. I'm a math person for a reason. Words are not my thing. So let's just do a bunch of examples and see what we got. Okay, let's take all of that wonderful knowledge and answer some questions. I made all of these up. So the validity of, if you're wondering, well, am I going to see this exact same problem on an AP exam? No, but these are the types of problems that you see on like AP Classroom. These are the types of problems that you see from practice exams that College Board makes. This is what you would see. I just pulled a bunch of pictures from the internet and created my own problems based off of those pictures. So A, on which interval or intervals is the rate of change increasing? We know from the first thing that we looked at that when the rate of change is increasing, that's concave up. So on which interval or intervals do we see concave up? Only between U and U. So that interval is going to have between 1, but not including 1, just 1, not including 1, because technically here, I have no rate. It's 0. But it's going to be between 1 and 6. And that's the only part on this whole thing that I have concave up. Okay? B, on what interval is the function decreasing at a constant rate? Notice how I said the function is decreasing and not the rate of change is increasing. If my function is decreasing, that means that's happening. So that interval takes place between 6 and 7. So we're going to say the interval 6 and 7. Okay? Find the average rate of change on the interval 2, 5. Now, in the second slide, when we talked about the average rate of change, we wrote out a formula. We're not going to write out a formula here. What we're going to do is we're going to find the interval 2, so that gives us that point right there, and we're going to find the interval 5, which gives us that point right there. Okay, now the average rate of change is the same thing as slope. So the average rate of change is going to be the slope connecting those two dots if I knew how to draw a straight line. Down 1, 2, 3, right 1, 2, 3. The average rate of change is negative because it's a negative slope, 3 over 3, which is the same thing as negative 1. No calculations needed. Also, find an interval where the average rate of change is 0. If the average rate of change is 0, that means you get yourself a horizontal line. So there's several places that I can do that. I could do from here to here. That gives me a horizontal line. Boom. I could do from here to here. That gives me a horizontal line. Boom. Boom. I could do boom. If I really wanted to, I could try to predict what that is, but I'm not going to. So I have a bunch of different options. The option that I'm going to choose is between from this guy to this guy. So between 2 and what is that? 6. Between 2 and 6, I have an average rate of change of 0 because it's flat. Okay? Questions? You're on YouTube. But you can comment. That helps me out. And of course. New problem. Show that the function is quadratic. Oh, my face might get in the way. Let's see. I don't want to move it because it's so nice. We'll see. Let's make sure that my x values are going up by the same number every time. So +1, +1, +1, blah, 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 hooray. So let's test linear. I know it's not linear because I already know it's quadratic. We need to show that it's quadratic. So what do I do? To get from 6 to 0, subtract 6. Subtract 4. Subtract 2. Nothing. That was supposed to be a 0 and it didn't turn out to be. Add 2. Add 4. Add 6. Oh, perfect. Nailed it. Now you can see the pattern forming. However, since this number is not the same throughout, it's not linear. So when we test out its quadraticness, which is a word, we're going to be like, okay, well, let's do it again. Let's add 2. Let's add 2. Let's add 2 again. Add 2 again. Add 2 again. Add 2 again. Add 2, add 2. It is quadratic. And the way you would explain that on like an open-ended problem is you would say that this is quadratic because the rate of change of the function over equal interval consecutive input values is 2. It's the same. Find the average rate of change on the interval -2, 2. All right, now I am going to use that formula. So let me remind you, if I call you A and if I call you B, I'm looking for f of B minus f of A over B minus A. Now, I know what B is and I know what A is. B is 2, so B is 2, and A is -2. All right, so the easy part is looking at the bottom. 2 minus -2 is going to be the bottom. F of B means I do f of 2, which is -4. So f of B is going to be -4. F of B is going to be -4 minus f of A is going to be when I plug in -2, which is 0. So -4 minus 0 is -4. 2 plus -2, double negative makes a positive, is going to be +4. I get -1 as my average rate of change on the interval. So if I were to graph all these dots and connect this point to that point, I'm going to get a slope of -1. Is the function concave up or concave down? It's quadratic. What do I know? The rate of change, remember, this is the rate of change. The rate of change comes from what your linear stuff is doing. The rate of change was -6, -4, -2, 0, positive, positive, bigger positive. My rate of change is increasing, which means concave up. My rate of change went from -6 and got bigger, 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 bigger. Since my rate of change is increasing, it's going to be concave up. Now to do the last problem, find f of 7, I have to use this information over here and keep this going. So I'm going to make you 5, I'm going to make you 6, and I'm going to make you 7. All right, so what we do to get from 0 to 6, what I did is I added 6. According to this guy, every time I add a number here, I have to add 2 more. So in order to get to 5, to find out f of 5, I add 8 more. And then I'm going to add plus 2, 10. And then I'm going to add plus 2, 12. So 6 plus 8 is 14. 14 plus 10 is 24, and 24 plus 12 is 36. F of 7 is, that's a 3, 36. Oh, I like these. I just love them. Just love them. Love them. Can't get enough. Show the table represents a linear function. Got it. Okay, I know what to do. If it's linear, then these numbers go up by the same time. Do these numbers go up by the same number? Yep, plus 1, plus 1, plus 1, plus 1. So this has to be the same thing. Oh, my face. I have to move it. Oh, wait, almost there. All right, so what am I doing? I am adding 3, adding 3, adding 3, and adding 3. This function is linear because the rate of change over consecutive input value equal intervals is 3. What is the average rate of change? Well, the average rate of change comes from the fact that I have a linear pattern of 3 over 1, so my average rate of change is a positive 3. When is the average rate of change increasing? Oh, wait a minute. If my rate of change is increasing, that would imply that I'm dealing with concave up. Well, this is linear, which means it's not concave up. So when is the average rate of change increasing? Never. Never. Sandlot. No, he says forever in Sandlot. Ooh, I'm embarrassed. Very similar to a previous problem that we did just like 2 minutes ago. I now need to find -5, which means I'm going to go back -3, I'm going to go back -4, and I'm going to go back to -5. If going this way was +3, then going this way is going to be -3, and then -3, and then -3 again. So -7 minus 3 is -10. -10 minus 3 is -13. -13 minus 3 is -16. F of -5 is -16. So far, we do these without knowing that we have calculators that can do linear regression and quadratic regression. If those words are new to you, we will do linear regression and quadratic regression at some point. We're just not there yet. We're pretending we don't know. And a lot of these problems would show up on a no calculator section of an AP exam anyway. Moving on. Did it work? It worked. All right. Name the 2 inflection points. Look at this mess. Concave up, concave down, still concave down, concave up. Interesting. Concave up, concave down, still concave down, concave up. And if you're like, well, what about E? What about E? Inflection points occur when there's a change in concavity. Did I change concavity when I went from concave down to concave down? No, 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 no. This was concave up, concave down, concave down, concave up. Name an interval where the rate of change is positive and increasing. Rate of change is positive and increasing implies concave up. So if it's positive and it implies concave up, we're looking for something that looks like this. So where do I see an interval that looks like this? I see 2, actually. 2 intervals that look like that. Here and here. So let's name both of them. Let's name both of them. Let's name between A and B, not including A, not including B, union, and H to forever. So we're going to say H to infinity. Now, technically, I guess this is dangerous because we're assuming that this is just going to keep on increasing forever. But I stole the problem from the internet, so let me make that decision and tell you, yes, friends. Here, let's do that. Happy now? I am. Name an interval with a negative average rate of change. A negative average rate of change implies that it is a negative slope. This is not implying concave down. Decreasing rate of change implies concave down. Negative rate of change or negative average rate of change implies if I were to draw a line from that dot to that dot, am I going to get a straight line going down and to the right? And we have a bunch. Between C and E does that. Between F and G does that, and between F and H does that. So let's name them all. And technically, negative infinity to A does that. So for funsies, let's name them all. Negative infinity to A, union. C to E, union. F to G, union. G to H, union, and F to H. Wow, sir, you must be a teacher. You keep saying union a lot. No, I live in Philadelphia. So go union. Live near Philadelphia, 30 minutes away. What is the average rate of change on interval E, G? Here's E. To get to G, it's just a straight horizontal line. Well, that's 0, boys and girls. Moving on to the next one. A couple more, I think 2 more. Maybe 3 more. On what interval is the function decreasing at a constant rate? The function is decreasing, not the rate of change. So if the function is decreasing at a constant rate, constant implies straight line. That's happening from 2.5 to positive infinity. On what interval is the rate of change positive and decreasing? Rate of change is positive, and decreasing implies it's increasing, and it's also concave down, which gives you the left side of concave down. So the
All right, so I made a little mistake here. I accidentally said that the answer is -1 to 0. It's actually 0 to 1. That's the left side of concave down. Whoopsie daisy.
Name the 2 intervals that have the same positive average rate of change. All right, so let's get rid of the few colors that I added here. Same positive average rates of change. Okay, so you're a negative rate of change, you're a negative rate of change, negative, negative, negative. Well, that makes life a whole lot easier because between here and here, I go up 2 over 2, and between here and here, I also go up 2 over 2. I should say up 2 units over 2 units, because if you really look at this graph, it's actually not up 2 over 2, and that's going to bite us when we do D. All right, so we will say the 2 intervals are going to be between -1 and 0, union, and between 0 and regular 1. Pause it if you have to, because I'm erasing it. Rewind it if you have to, because I erased it. What intervals is the average rate of change -1? All right, so we have a negative average rate of change. So I can't tell. Maybe you're positive, maybe, can't tell. All right, so I have 3 options here. If I were to connect this dot to this dot, that looks like it should be it because you go down 2 units, right 2 units. When you go down 2 units, you go down -2 because each unit on the y-axis moves by 1. But each unit on the x-axis goes by 1/2. So this is actually down 2, right 1/2, 1. Tricky, tricky, tricky. So if the slope looks like 1, it ain't. So that gets rid of u and leaves what must be u. Down 1 over 1, 2 units, which means down 1 over 1, -1 over 1 is -1. And that happens between 1.5 and 2.5. Tricky. Oh, so tricky. Two more. The function, maybe 3 more? Is the function linear or quadratic? All right, well, I've done a bunch of these, so let's just fly through them. Is the function linear or quadratic? Well, let's test its linearity. So -5, -3, no, it's not linear, -1, +1, +3, +5. It ain't linear. +2, +2, +2, +2, +2. At this stage, it's just like, just muscle memory. If the function is quadratic, it is it concave up or concave down? Well, if I want to look at my rate of change, I'm looking at my linear behavior. Shame on me, I should have made sure that these guys go up by the same number they do. If I wanted to check my rate of change, I look at my linear behavior. My rate of change goes from -4 to -3 to -1 to +1 to 3 to 5. Oh, those numbers are going up, which means my rate of change is increasing. So it's concave up. Find the zeros. The zeros are when my graph crosses the x-axis, which means my zeros exist when my y, or f of x, is 0. My f of x is 0 when x is 1, and my f of x is 0 when x is 5. Similarly but opposite, my y-intercept occurs when x is 0. So when is x 0? Only once. When f of x is 5. What is the average rate of change on interval 1, 6? Well, I'm going to use the formula again. F of b minus f of a over b minus a. That is my interval. So I'm going to call a 1, which means f of a is 0. And I'm going to call b 6, which means f of b is 5. F of b is 5 minus f of a is nothing, easy, over b is 6 minus a is 1. 5 over 5, last time I checked. Decaybe Matumbo, not in my house. It is 9:15, and I've been awake for 14 hours. No, 15 hours. 15 and a half. Does the table represent a linear or quadratic relationship? For the first time, these numbers don't go up by the same number. This is not consecutive input value equal intervals, spaces, or whatever. It ain't. Okay? So I can't use the let's do the bunny hops and see if the numbers are the same. Can't do it. This is what I can do, though. Okay? Remember that slope is found by the change in y values over the change in x values. This would be an x value. This would be a y value. Okay, so if I wanted to find the slope between these 2 points, I would do the fact that my change in x value is going to be from 1 to 3, 2, so plus 2, and my change in y value is positive 8. So my slope is going to be the change in y, 8, over the change in x, 2. 8 over 2 is 4. And then I do it again. I do it again because that's not good enough for me to make a determination as to whether or not this is linear or quadratic. If it's the same and it's the same again, it's linear. If it's not, it could be quadratic. Let's pray that it is linear. To get from 3 to 6, I add 3. To get from 9 to 21, I add 14. No, 12. I just got so excited for 21. My change in y over my change in x is 12 over 3. 4 again. Oh, PTL. That stands for praise the Lord. Let's do it again. To get from 6 to 11, I add 5. To get from 21 to 41, I add 20. My y value changes at 20. My x value changes at 5, 4. The rate of change is the same for all 3 possibilities. Therefore, it's linear. Good. I can't imagine you ever being given a problem where this problem is going to be quadratic when you don't have spaces in between. I can't imagine. I do know that it's linear. The rate of change is 4 every time. What is the rate of change of the rate of change? Well, that implies that it's quadratic. So it's linear. If it's linear, the rate of change means what's this number right here for quadratic? Well, the number for quadratic is going to be 0, no matter what. Even if I were to write these all out perfectly, it's going to be 0. So what's the rate of change of the rate of change? 0. If I give you a linear function, the rate of change of the rate of change is 0, which means acceleration is 0. In this case, it's meters per second is 0. And yes, I said that correctly. If you're talking about rate of change, you would write that out as meters per second, or meters per second squared. Okay, and that is what we consider acceleration. So this guy's going the same speed the whole time. The same speed, 4 meters per second the whole time. It doesn't speed up, it doesn't slow down. So predict the distance at 14 seconds. Okay, well, at 12 seconds, we're going to add 4 more, so that gives me 45. And at 13 seconds, we're going to add 4 more, so that gets me 49. And at 14 seconds, we're going to add 4 more, so that gives me 53. So the distance at 14 seconds is going to be 53 meters. Kind of a gross problem, and it looks gross. But we have one more to go, and then we're done. Oh, hooray. We finally, hold on. We finally get to use our graphing calculator. And so we're going to do that. Okay, we're going to use our graphing calculator. You get a nice little picture here, but sometimes the pictures aren't good enough. If you remember a lot of quadratics from Algebra 2, you know what's going to happen. You know what zeros are, and you know what factoring is, but we're going to pretend that we don't, and we're going to rely solely on our calculators. So I wonder what this is going to look like on our calculator. All right. We are using a TI-84 plus CE color edition to graph the function that we're given. So, and whenever you want to graph, you're going to hit y equals. Now, the frustrating thing right off the bat is we start out with a negative. Now, the only place on the planet where a negative and a minus sign are different is the Texas Instrument family of calculators. Everywhere else, it's the same, but you know, with Texas Instruments, they decided to make it a little more fun. But let's keep typing x, parentheses, of course. Here's my x right here, x minus 3, close parentheses, x plus 7. Now, what we're going to do first is we're going to get ourselves the graph. Bada bing. Now, this is the graph that you see already included on the slides that I have for you. But, you know, one of the things that we need to find is we need to find exactly where the zeros are. And then at one point, we need to estimate intervals, which requires us to find some more information. So we could find the zeros. We know the zeros by looking at the parentheses. But if we really need to be specific, and if we're allowed to use calculators and we need to find zeros, this is one way to do it. Hit second, trace, and that takes you to calc. Now the second option right there is 0. So we're going to click that. Now I know I have a 0 right there. So when it says left bound, what I need to do is I need to place a little blinking thing that I don't see yet to the left of my 0. Now right now my blinking thing that I don't see is at x equals 0, which is here. So it's going to be way up here where I can't see it. So I'm going to hit left a bunch of times until it goes to the left of my 0. Eventually it'll show up very soon. There you are. So I'm going to go to the left of my 0, hit enter. For the right bound, I'm going to go to the right of my 0. I have to make sure I cross the x-axis, and this is showing me an interval where my 0 lives. For guess, you always hit enter, and I should get a 0 of -7. I do get a 0 of -7, and we can see that. Now we're expecting a 0 of 3, so let's just make sure that that's the case. If I want to find the 0 of this one, you're going to hit second, trace again, that takes you to calc. Hit 2 or go down to 2 for 0, And we're going to do the same thing, but make sure we see our little blinky thing somewhere to the left of our 0. So we can't see it. X is still negative. So once it hits around the 1, 2 area, we should be able to see our blinking cursor, and there it is. Let's make sure it's to the left of where our 0 appears to be. Once you have that, hit enter. Now move to the right. You have to cross the x-axis, otherwise there's no sign change. There's an interval. Hit right again. And our other 0 is 3. Oh, great, we did it right. Okay, so in order for us to determine where the interval is increasing or decreasing or whatever, we need to find out where that increasing and decreasing changes. So if I go to graph, I see here that it's increasing. Somewhere up here it changes and then it starts decreasing again. Well, I need to know exactly where that change is. So what I can do is I can click zoom and zoom out. Once you do that, select 3, hit enter, and there you have exactly where you need to be. Here's the issue. I can't tell exactly where my maximum is. So you remember, at some point, I'm increasing, and right around here, I stop increasing and start decreasing. So I need to find the x value of right around here. Well, in the last example that you saw, we had to calculate. So I'm going to hit second trace, and it gives me more options. Now, the one that I want is maximum, because where things change is at the maximum peak of my graph. So I can go down to 4 or I can hit 4. And just like I did with the zeros, I need to make sure that my cursor is to the left of my maximum. So my maximum is up here. That's where things change. So my cursor is to the left of the maximum. I hit enter. I go to the right past my maximum and then hit enter again. It shows me an interval where my maximum should be. When it says guess, always hit enter. And it tells me that my maximum is negative 1.99999999999. Now, I'm no mathematician, but I'm pretty sure that negative 1.999999999 is negative 2. So when I do this problem, I know that all the magic happens at negative 2, and that's going to be my change in interval. What is the average rate of change on the interval negative 3 and 1, you ask? Well, if I hit graph, I can't really see what I have. Now, if you've noticed, you might be thinking, oh, this is the same exact way the graph looked in the problem when you zoomed out. Let's zoom back in. Well, I'm going to go to zoom and I'm going to choose standard because that gives me a regular looking thing. Here's an issue though. If I'm trying to find where action happens in between negative 3 and 1, I have no clue what's happening at negative 3 because it's way off screen. I need to find what's going on at negative 3 when I plug in negative 3. So here's an option. If I go to second table, I can find out what's going on when x is negative 3. Right now, I can't see it. But if I scroll up a little bit, I know that when x is negative 3, f of negative 3 is going to be 24. I also care about what's going on at f of 1. So at f of 1, I have 16. So f of negative 3 is 24. F of 1 is 16. I should be able to do my calculations now.